Good afternoon, Prof. My name is Iqbal, and together with me are Chia Chun, Hui Xiang, Nathaniel, Hilman, and Joe. We are from Group 17, and we will take you through our IoT project titled Solar Grow Greenhouse. We will start by going through the background, problem statement, followed by the proposed solution. We will then elaborate further on the design and key innovation. We will then discuss the challenges and future implementations that can be developed for our idea. So let's begin. We will first talk about the background research and the problem statement. So first and foremost, what are greenhouses? Greenhouses are essentially structures that are made of glass or some transparent material that are used to cultivate plants in a controlled environment. The controlled environment are achieved through temperature control, humidity control, pest control, weather control, and environment control. However, greenhouses face several challenges in bringing about its intended functions. Some of the common challenges faced by greenhouses include temperature control, which can be challenging as greenhouses can overheat during the day, pests, watering and fertigation, as well as lighting. So for our project, we would like to put a focus on tackling the temperature and lighting challenges faced by greenhouses. Did you know that plants grow best when they are exposed to a certain range of temperatures and light? Based on our background research, the temperature range for optimal growth of plants is around 64 to 75 degrees Fahrenheit or 18 to 24 degrees Celsius, and the optimal light exposure is between 2500 and 7500 lux. So how do greenhouses achieve these conditions? Well, for temperature, they use fans, vents, and wet walls, and for light, they use artificial light. However, there are some limitations of the current measures. For temperature, it can be affected by extreme weather and fluctuates, and for light, there are the presence of shadow zones which will affect the optimal growth of the plants. So this leads us to our problem statement. Why is temperature and uneven light distribution a challenge faced by greenhouses, and how can we use IoT systems to achieve optimal growth? I will now hand over the time to Chia Chun, who will go through with you on the proposed solution. Thank you.
Thank you, Iqbal. I'll be sharing the proposed solution. So, what is our requirement of the greenhouse? We aim to be self-sustainable and smart so as to reduce human intervention as much as possible. And for our feature of the greenhouse, we have an adjustable prismatic glass which uses a light sensor which is paired with a servo motor and LCD. A second feature is the automated shutter which uses temperature sensor together with the smart relay and the buzzer. Here's the component used. And for the light sensor, it is used together with the servo motor to trigger the glass prism mechanism, and it also displays the light lux value on the LCD. Furthermore, the temperature sensor is used to trigger the smart relay, which closes the shutter and trigger the buzzer when it is too hot. And furthermore, it is also displayed on the LCD. For your reference, we have the circuit diagram for temperature sensor, light sensor, and buzzer, and the smart relay, servo motor, and LCD. For the ThinkSpeak channel, we collect temperature and light data before storing it in ThinkSpeak cloud and is viewed by the four other components. For our channel, field 1 is used for temperature and field 2 is used for light intensity or lux. For our channel, it is private so as to allow accessibility for the farmers or worker. And we also develop a smart greenhouse application that can track temperature data, light data, view a CCTV footage of the greenhouse, and the component status of the light and temperature sensor. Next, I'll hand over to Ned to talk about the component.
Thank you, Jiajun, for sharing. Next, I'll be going through elaboration of design. So the chosen component used for the IoT projects are temperature sensor, light sensor, servo motor, smart relay, LCD, and buzzer. Next is the REST API system. As for the system used in the IoT project, the team has decided to use REST API system. As for how it works, through REST API, they uploads the data into ThinkSpeak channel. The client, which is the servo motor, smart relay, LCD, and buzzer, would request the information in the ThinkSpeak channel, and the server, which is the temperature and light sensor, will upload the data onto ThinkSpeak. Next is the temperature sensor, and the function of it is to measure the ambient temperature in the greenhouse. For functionality in IoT is to measure the temperature and upload its data onto a ThinkSpeak channel where the data can then be read from. Next is the I/O map for the temperature sensor. As mentioned in the background research and proposed solution, plant growth is optimal when the temperature in the greenhouse is around 18 to 24 degrees Celsius. Hence, the above table, we can see the threshold value are set according to those temperature. And however, due to the demonstration purposes, we have created a new range. As for the buzzer, the function of the buzzer is to convert audio signals to sound signals, and the functionality in IoT is to buzz when it's opening and closing of shutters. Next is the smart relay. The function of the smart relay is basically a switch which is normally open and has the indicator when a terminal is closed. The functionality in IoT is the switch is closed when temperature threshold has been breached in the greenhouse. And green will mean that the switch is closed and red will mean that the switch is open. Next is the light sensor. The function is to measure the ambient lux in the greenhouse. Functionality in IoT is the light intensity values are uploaded onto ThinkSpeak channel field 2 where the data can be read from. For the I/O map of light sensor, the ideal range is 410 to 614 lux, and the RGB will turn green, LC will turn red, and the above table will be the value used for the demo. Next is the servo motor. The function is to rotate clockwise and counterclockwise, and the functionality in IoT is to serve as the servo motor which receives data from ThinkSpeak with the lux value by light sensor, and the motor will rotate the prism glass panel until the ideal lux value is achieved. Next is LCD. The function is to display message on the screen, and the functionality of IoT is to read both value of light and temperature field on ThinkSpeak channel and print the value onto the LCD screen accordingly.
Thank you, Ned, and now I'll be going through more about the key innovation. So, for our key innovation, I'll briefly go through how it works. Initially, when sunlight from the sun comes into contact with the dome, the rays will go through as in. This brings forth the aforementioned problem, the formation of the shadow zones. Adding of the prism slates sandwiched between the exterior and interior wall will allow the sun rays to be refracted in such a way that it also distributes to the shadow zones. An expanded view of how it works can be seen here, where the incoming rays will be split into those refracted to the dark zones as well as others straight as per usual. Next, I would like to describe the sequence of events. First, the light sensor will measure the lux value from the sunlight. The servo motor will then receive the lux value and start adjusting the angle of the prism in the sandwich layer such that the lux value reaches an optimal value. Now, this brings me to my next point. How does this solve the problem? First, less energy consumption. The motor is only triggered only when needed to dissipate light. Next, less power is consumed, unlike artificial lighting, which is currently in the market, which is when used, it is turned on longer. Efficient lighting in greenhouse. The use of glass prisms would then be able to effectively disperse natural light all over the areas in the greenhouse, eliminating dark zones. Thank you. Now I'll pass my time on to Human.
Thank you, Hui Xiang. I will now be discussing about the challenges we faced during the project. One challenge is that there is a 15-second delay on the ThinkSpeak channel. Hence, we are unable to see the changes in real time due to the 15 seconds interval. This is because we are using a free account on ThinkSpeak which has many constraints. Another challenge is that the dependent component on the IoT system. For example, if a component is down, we will not know if the system is running as they depend on one another. To overcome this challenge, we use GUI to indicate whether the system is failing. This is done by checking the field graph to see if it's being updated. Lastly, in our system designed for the key innovation, the movement of the glass panel will increase the temperature of the greenhouse. This will make the greenhouse even hotter and might exceed the optimal temperature. To tackle this issue, we have created an automated shutter system using a temperature sensor, smart relay, and the buzzer. When the temperature sensor senses that the temperature is not optimal, the smart relay will trigger the shutter to close and the buzzer will start buzzing for safety purposes. I will now summarize our project before we head into our future improvement. We use different components and sensors to link them out using IoT. This is to create a real-time monitoring system. We also created a GUI to read the fields from the channel and to showcase the current update of the system. I will now pass the time to Joe to discuss more about the future improvement.
Thank you, Hilman. Now we'll be going through our future improvements to the system. Firstly, for improvements to our IoT system, because our team is using a free ThinkSpeak system, we have a 15-second time delay between publishing and receiving. Upgrading to Hive MQTT will allow true real-time updating and allow faster response times, improving on the challenges that Hilman has mentioned. We can also implement Google Apps Script. GAS provides seamless integration with other Google services such as Google Sheets and Google Drive. This makes it a good choice for greenhouses where there is a lot of data generated and collected. For instance, GAS can automatically collect our IoT data and generate a report on the health and the productivity of our plants, and email us the report in real time. Next, we can implement MQTT and GAS into our systems as so, where MQTT is replacing REST API in order to allow us real-time access to our data, and GAS will be collecting the data from the MQTT system in order to conduct data collection and analytics. Next, for our improvements to the system, we can start by implementing moisture sensors to the soil, which are connected to water sprinklers and they activate when low moistures are detected in the soil. This allows us to establish a fully automated greenhouse system and alleviates manpower needs. We can also increase the quantity of components in the system, increasing redundancy and improving reliability. Thank you, Prof, for your kind attention.